Okay, well today we're going to continue our topic of reactions, that is by looking at the reactions of dienes. Recall this is where we left off last time. We really didn't get into it, but now let's see what's going on. Remember from Organic Chemistry Part 1 that we learned the reactions of alkenes. Recall if we took propene, for example, and reacted it with HCl. HCl, remember, has a dipole moment in this direction, to thereby giving us partial charges on the hydrogen and the chlorine. So the hydrogen has a partial positive, the chlorine has a partial negative. The alkene with the double bond, remember that we could draw a lone pair in there for the pi bond. That is, the pi bond can act like a lone pair, and so it can act like a base. And so this kind of alkene reaction is really an acid-base reaction. And remember, our mechanism for acid-base reactions is that the lone pair, or here the pi electrons, attack the delta plus on the hydrogen, and the chlorine gets kicked off. So if we do that, we note that we have two possibilities of where to add the hydrogen. The hydrogen could add here, or it could add here. If the hydrogen adds on the less substituted carbon, then what? The more substituted carbon forms a positive charge, and so we get a carbocation intermediate. If the hydrogen had added here to the more substituted carbon, then what? The less substituted carbon would get the positive charge. Do you remember which of these two was the more stable one? Yes, it was the more substituted positive charge. And so the mechanism is going to go by this route and not this route. Okay, so we'll go ahead and cross this one off, and we'll stick with the more stable carbocation. Chlorine got kicked off as Cl minus. So what is it going to do? It's going to attack the positive charge. And so the chlorine ends up on the more substituted carbon. And remember, this follows what was called Markovnikov's rule. So what was Markovnikov's rule? It says the major product was dictated by the more stable carbocation forming in the intermediate. And so this was our recollection of an alkene reacting with an electrophile such as HCl. So with this review in mind, let's go ahead and tackle dienes and see how they react. We'll see they react in the exact same way. So let's take a diene. Such as 1,4-butadiene. And let's react this with HCl. Okay. So here again, we have an alkene with HCl. Let's just look at one of the double bonds. Let's choose this one here and draw the lone pair on it, so the attacking will be done from it. So again, it's going to attack the hydrogen and kick off the chlorine. What is the result? Well, again, we have two options where to put that hydrogen. We learned last time where it's going to go. It's going to go here, right? So that the more substituted carbon, the secondary, forms the positive charge. And so here is our carbocation intermediate. But if you look at this intermediate, what do we have here? It's what? The classic definition of an allylic carbocation that we learned last time with resonance theory. So here, what we can draw is a resonance structure. Where the pi electrons move over and the positive charge trades to that outside carbon. So this is the big difference between dienes and regular alkenes, which is one double bond, is that the conjugation allows us to get two different carbocation intermediates. And because of that, the chlorine, the Cl minus, can attack either one. So in the second step, if it attacks this one, we get this product. And over here, if it attacks that one, we get that product. So with the diene setup, we can form two different products. And when we have two different products, we always ask which one forms more, or which is called the major product. And that's what we want to try to figure out. But before we do that, let's label these, give these products different names. This product here, where the chlorine and the hydrogen added as neighbors, this is called the 1,2 product. Okay? So 1,2 referring to neighbors, whereas over here, the hydrogen and the chlorine added 1,4, so we call this the 1,4 product. Okay? So that's one way to classify these two products. Another way is that this one here is also called the kinetic product. And this one over here is called the thermodynamic product. Okay? So let's see what these two terms mean. When we have the kinetic product, it is the product that forms the fastest. Okay? When we have a thermodynamic product, what we say by it is that it is the more stable product. Okay? So let's see if we can answer why does this one form faster and why is this one the more stable product. Okay? Well, this one forms faster because if you look at the two carbocations, this one was more stable, and so this pathway is going to form faster because this forms easier, then this is going to form easier. So the kinetic product has to deal with the carbocation intermediate. So since this one is the more stable intermediate, this product here forms the fastest. Whereas for the thermodynamic product, it is the more stable product, not the intermediate, the product. Why? Because the double bond that forms is more stable. Okay? This here is what a 1,2, a di-substituted double bond. And this one here is a mono-substituted double bond. So this double bond is more stable, and so this product is more stable, and so we term it the thermodynamic product. So that's how we can classify these, but we still haven't answered which one is the major product. How do we answer that? Well, that answer is due to temperature. Okay? We can have two realms of temperature that we are talking about. We can have what's called low temperature and high temperature. If we're doing the reaction at low temperature, the kinetic product is the major product. Okay? If we're doing the reaction at high temperature, the thermodynamic product is the major product. Okay? You might ask, why is that the case? Well, the reason is because the kinetic product has a smaller activation energy. And so if I use a low temperature, this smaller activation energy, which is formed because this is the more stable intermediate, since this activation energy is smaller, a low temperature can be used, and that can be the major product. Over here, for the thermodynamic product, this is a lower stability carbocation, and so the activation energy will be higher. And since I have a higher activation energy, I'm going to have to use a higher temperature to get over that hill compared to this one. And so at higher temperature, this one can form, and once this one forms, we're locked in because of its high stability. So that's how we can depict which product is going to be the major product with these Diene reactions. Okay? So make sure you understand the terminology and the stability all the way through the different pathways and which one is the major and minor product at those temperatures. Okay, well, let's move on then. And let's look at another reaction. Okay. Here we're going to look at what's called allylic bromination. Allylic bromination. Let's draw an alkene, something like that. When we have a double bond, the carbon next door to the double bond is the allylic carbon. Okay? And what we can do is brominate, add a bromine to that allylic carbon by using a reactant called NBS and some heat. And we get a bromine atom on that allylic carbon. The structure of NBS is this thing here, where the bromine is on the nitrogen, so that is what gets transferred to the allylic carbon. And the structure is what's called N-bromosuccinimide, and we abbreviate it NBS through this N, this B, and this S here. So just the acronym is a lot easier to say than N-bromosuccinimide, but you want to know the name and the structure that's associated with it. We'll be using NBS later on in another chapter to look at another type of allylic bromination. Okay? But for now, just remember, this adds a bromine to the carbon adjacent to any double bond. Okay? Let's go on and look at something else here. In our chapter, the next thing we want to look at is a little different kind of reaction. Something called the Diels Alder reaction. The Diels Alder reaction. This is a very popular reaction in organic chemistry, and it's one that occurs in the natural realm as well. So let's see what this reaction is about. It's totally different than what we've been studying. This kind of reaction involves one molecule that is a diene and another reactant that's called a dienophile. Okay? So we have the diene, two double bonds that are conjugated. In the dienophile. Why is it called that? Because it loves the phile, the diene, it loves the diene. So the two are going to react with each other. One comment to make about the dienophile is that it usually has electronegative groups or electron withdrawing groups on the double bond. So the diene, the dienophile, is going to be a double bond, one double bond, that reacts with the diene, where we have two conjugated double bonds. So how do these two react? Well, what I like to do is call this a dog chasing its tail. So the mechanism is these pi electrons are going to form a bond here. These pi electrons will form a bond here, and these will move right here. So if we draw the result of this circular mechanism, we end up forming a ring where the double bond has moved here, and this bond and this bond are the new bonds that have formed. Okay? And so note we get a cyclic molecule with this Diels Alder reaction. Okay? So that's what we want to do, is look at a bunch of these from the chapter and start to get a feel of them. So let's look at another one. Another Diels Alder reaction could be something like this. Where if you note now, we have our diene, but our dienophile is now a triple bond. Okay? So how do we tackle something like this? Well, we do it the exact same way that the pi electrons move, so that it's like a dog chasing its tail. So let's draw the result of this one. Okay. Again, we form this six-membered ring, but what's the only difference? The only difference is we use one of these sets of pi electrons, so we're still going to have a set left behind, and so we'll have a double bond here in this case. Okay? So I can know that I started with a triple bond if I have a double bond left behind. Okay? So a dienophile can either be a double or a triple bond, and again, they always stick out because they have these electronegative groups on them. Let's look at another one. Let's look at this reaction here. Okay. So this time our diene is trapped in a ring, and here we have our dienophile, but this time we have two new electronegative groups. Okay, carbonyls this time, or cyano groups that we saw the last two times, can act as nice electron withdrawing groups. So what do we do here? Well, we do the exact same thing. We form a bond here, we form a bond here, and those electrons go there. So it's the exact same thing that we did as last time. So let's draw the structure. Let me draw it for you and then come back and explain, as it's probably going to catch you off guard. So why don't you go ahead and draw that. Give you some new artistic bent there. Okay. Might be saying, what in the world is that? That's okay. Just go ahead and do your best to draw this, and then we'll explain how this interesting structure here formed. If you note, our new bonds are here and here. So let's draw the carbon atoms that got attached here, 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 and here. Where are the carbons over here? Well, they're right here and here. So we call these our A carbons. They're right there. And the B carbons are over here. Okay, so our double bond was over there. And this carbon here that's sticking up, okay, that's this one here that was not used in the reaction, so we just draw it and get it out of the way. Now, this is a three-dimensional drawing of the molecule. We could redraw this to something like this. Okay. Could redraw it like this, where we draw it just two-dimensionally, where it looks like a flat pancake. And yes, it doesn't matter whether I draw the carbonyl up or I draw it down. It's the same thing, because this bond here is rotating easily. You might say, well, why didn't you draw the structure like this to begin with? Well, I just wanted to bedazzle you a little bit by getting you shell-shocked so that you're not shocked in the future when you see drawings like that. Okay? So these are Diels Alder reactions that you want to be familiar with. And what you want to be familiar with is if I give you the diene and the dienophile, to not only be able to draw the product, and yes, you could draw it like this or like that, either way is fine. But you also want to be able to go backwards, so that if I give you this structure here, you should be able to draw for me what the original diene and the original dienophile was. Okay? So you want to work going both ways so that you can keep things under control. Okay? And so expect both ways on the exam. One last thing about these Diels Alder reactions. Is if I just used a regular linear diene, such as that, there are two ways to draw this diene. Okay? So I could draw it like this, the zigzag motion. Or I could draw them so that the two double bonds are on the same side. Okay? This single bond easily rotates, and so we can get either conformation. These two conformations are given names. Okay? What you want to do is keep your focus there on that single bond. If I look at this single bond, these two double bonds are on opposite sides. So this is what's called the S-trans diene, whereas over here, this is called the S-cis diene. What do you think the S stands for? Yes, it stands for that single bond. Okay, so we're trans about it or cis about it. Which do you think we use for the Diels Alder reaction? Okay, you probably saw it as we draw it earlier. It's the S-cis. Why do we want to use the S-cis? Because both carbons, both terminal carbons, are on the same side, so they can form the attachment to the dienophile very easily. Okay, so we always use the S-cis for Diels Alder reactions. Okay, so that's all we're going to say for Diels Alder reactions. What we're going to turn our attention to now is a totally different topic in this chapter. Okay, and here what we're going to look at is not really a reaction, but is more theoretical in nature. And this is what we're going to call molecular orbital theory, or sometimes abbreviated MO theory. Okay? MO theory. So this is a very important theory that we want to master in this chapter. Okay? As we'll be using it off and on throughout the rest of the course. Okay? So to get started with molecular orbital theory, okay, let's do a review of the p orbital. Remember the p orbital, it has this kind of shape here that we learned back in general chemistry. And remember, when we're looking at a p orbital, that we have an electron in it that is basically swimming from this side to this side and back. And if you looked at all the swimming motion, it would end up giving a shape of something like this. And this dumbbell shape, or this p orbital, is what we want to investigate a little bit. Well, when we draw this shape, we say that the two lobes have what are called different phases. Okay? That is, we can call one a plus phase and the other a minus phase. These have nothing to do with charges, so just get that out of your head right now. But these are different phases of electrons. Or sometimes we can use shading. We usually shade the positive phase in and leave the minus phase unshaded. Okay? So what does this phasing refer to? Well, it refers to the wave motion that the electron is moving in. So if I draw a positive phase, the electron, we can picture, maybe moving in a wave, something like that. Whereas in the negative phase down here, now the electron would be traveling something like that. Do you see the difference in the two phases? You see how this one, when it's going up, this one is going down, and so on. Okay? So remember, the height of the wave is what's called the amplitude. Okay? So here we're looking at amplitudes like that and amplitudes like that. Okay? So here we say that these two phases are 180 degrees out of phase. Okay? So they're 180 degrees out of phase when one amplitude is up and the other amplitude is down. Do you see what happens when the two waves collide with each other? What happens? This amplitude would cancel with that amplitude. You see that? And the same thing with these other ones. So what would be the result? Is that we would get a wave that would look something like this when these two collided. You say, well, what kind of wave is that? Is that still a wave? Yeah, it's still a wave, but how would you describe it? It's a wave that has zero amplitude. Okay? It has no height and no depth to it. And when we say we have a wave of zero amplitude, this is what's called a node. A node. Do you see where the node is in the p orbital? Yeah, it's right there in the middle. Okay? Because there's no thickness at that point. It's just simply a point. Okay? So the node is right there. That's what we get every time we have a plus and a negative phase colliding. We always get a node at that point. And you get nodes and other types of waves as well. If you have two radio waves that have interference, they'll collide and they cancel each other out. And at that particular point, wherever you are, you can't hear that radio signal anymore. Okay? And there's other types of nodes that you experience with other different wavelengths that are out there. Okay? So what we're going to do is use this theory of the p orbital and start looking at it an extra step by seeing how it's included in what we call molecular orbital theory. And we'll pick up on that in our next lecture.